Quantum mechanics is a very peculiar theory because in this subject we have to spend a lot of time performing a huge amount of mathematical calculations. We have to spend a lot of time performing mathematical operations on abstract mathematical functions, and every now and then we can come up with some physical prediction that we can correlate with the external physical world. So you see that there is a lot of mathematical jargon and there are a lot of important concepts that we have to understand if we want to perform various quantum mechanical calculations. And one of the important concepts in this mathematical theory of quantum mechanics is that of the inner product. What is the inner product? That is what I want to discuss in today's video. What is the significance of the inner product? What does it actually mean, physically speaking, as far as a physical system is concerned? You see, the concept of the inner product is not very new. We were introduced to this particular concept much earlier in high school when our physics teacher talked about vectors. If you remember vectors, right? Vectors are supposedly some sort of a quantity that has a magnitude and a direction. And when our physics teacher was explaining the concept of vectors, he must have also explained there is something called a dot product or a scalar product. You see, in this three-dimensional Euclidean geometrical space, if I define two separate vectors, A, let's suppose A is equal to AX, I cap plus AY, J cap plus AZ, K cap, and I have another vector B where B is equal to BX I cap plus BY J cap plus BZ K cap, then we can define something called a dot product where the dot product of A and B is simply equal to the summation of the product of their individual terms or the individual components along the x, y and z axis respectively. So that means this is AX BX plus AY BY plus AZ BZ, which is essentially a summation of the various components of A and B along the x, y and z axis. This dot product was defined only for vectors, for these kind of geometrical vectors. You see, in physics we have different kinds of physical quantities that can be represented by a vector. For example, force is a vector. If I ask a simple question that, let's suppose I have a particular force acting on an object in a specific direction, but what is the component of that force in a different direction? Now, the answer to that question is given by the dot product of the force with respect to the different direction. You see, the dot product gives us an idea about the projection of one vector onto another. It gives us an idea of the similarity between two different vectors. It gives us an idea about the overlap between different vectors. If the dot product of two vectors is 0, it means that those vectors are perpendicular. They are independent of one another. So the idea of a dot product gives us some information about whether two distinct vectors, how much of them are similar to one another. When we generalize this concept of a dot product or a scalar product for abstract vectors in linear vector space, that is where we come up with the concept of inner product. The inner product is essentially an idea that gives us some information about the overlap between two different quantum states. Now, in my previous lecture, I have mentioned to you that the quantum states are nothing but abstract vectors belonging to something called the Hilbert space. If you want more information on that, you have my previous video, you can check that video out. So the quantum states are essentially abstract vectors belonging to a Hilbert space, and the inner product, which by the way here is written in Dirac notation, gives us an idea about the overlap or the similarity between two distinct quantum states. And by doing that, it provides us with something very, very vital about the nature of the mechanism of the quantum mechanical theory, because not only this provides us with an idea about the overlap between states, it can also give us an idea about the evolution of a quantum mechanical state. And most importantly, it can give us an idea about probabilities if we make a measurement on the system. So therefore, this is very crucial in getting some idea about measurement outcomes or probabilities associated with measurement. So let us spend some time trying to understand what is the meaning of this inner product, so that in the future, for all purposes, the idea of an inner product is clear to us. Now, the manner in which I have written this inner product is using Dirac notation. This is how we write down the inner product. We have two different states. We put them inside this kind of a triangular bracket, and that is how we represent the inner product in quantum mechanics. However, there are different representations within the quantum mechanical theory. So you must have heard of the wave mechanical representation, right, as well as the matrix representation. So if we talk about the wave mechanical representation or wave mechanics, in which we essentially deal with the Schrödinger equation, the solution of the Schrödinger equation gives us wave function solutions. In that context, the inner product between two different states, let's suppose I have psi x and I have phi x, is simply written in this manner. I take the complex conjugate of psi, take its integral from minus infinity to plus infinity. This is what we do when we represent the wave functions as mathematical functions in position space. However, if we go from wave mechanics to, let's suppose, matrix mechanics, which is where we are heading forward. So in the matrix mechanical formulation or the Heisenberg formulation, the states are not necessarily represented by a mathematical function in position space, but they can be represented as vectors. They can be represented as matrices with respect to some abstract basis. So for example, if we are dealing with the electron spin, you know that the electron can have a up spin and a down spin, right, which is represented by the arrows in the up direction or the down direction. So the up spin is associated with a certain kind of a state which is represented by the up arrow, and the down spin is represented in this particular manner. But in matrix mechanics, the up spin is associated with a vector 1, 0, and the down spin is associated with a vector which is 0, 1. In matrix mechanics, this kind of an inner product is represented in this particular manner, and their answer comes out to be exactly equal to 0. What is the meaning of this 0? I'm going to come to that in just a moment. So you can see that as far as the wave mechanical representation is concerned, we are dealing with functions. Integrate the functions with respect to x if we are dealing with position representation. And as far as matrix mechanics is concerned, we are dealing with vectors. But what is the physical meaning of performing this kind of a calculation? I want to come to that, but before I do that, let me quickly mention some of the properties that we have to maintain while we are dealing with the concept of inner product in the context of quantum mechanics. So let us start with point number 1. Because in the context of quantum mechanics, we deal with situations in which there is interference that is possible for particles, or we can say superposition is possible. So the inner product preserves the property of quantum superposition, which is basically given by the idea of linearity with respect to the second argument. So if I take a linear sum of quantum states, so for example, if I say I have a state C1 phi 1 plus C2 phi 2, this is basically a superposition of two distinct states, and I take the inner product of that linear sum with respect to another state psi, then this inner product preserves that linearity with respect to the second factor or the second argument. So I can simplify this expression as C1, which is a scalar, will come out. I will have psi inner product phi 1, and I will have C2, which is a scalar coming out. I will have psi inner product phi 2. This seems like a very simple property, but we have to remind ourselves that we are in a very sort of an abstract mathematical world, and there in that particular world we have to be very precise about the kind of mathematical rules that we can follow or that we reject. Therefore, these are some properties that I'm mentioning. We will be maintaining them throughout all our dealings with the concept of quantum states. So, the inner product preserves this linearity with respect to the second factor, but it is antilinear with respect to the first factor. So, if I take C1 phi 1 plus C2 phi 2 as a bra and not as a ket, in that kind of a situation, it is antilinear with respect to the first argument, which means that all these scalars, as they come out of the inner product, they will basically be taken as a complex conjugate. So I take C1 star phi 1 psi plus C2 star phi 2 psi. This is because in quantum mechanics, the quantum states are complex quantities, complex mathematical functions or complex vectors. They don't necessarily have some sort of a physical meaning. So therefore, the inner product may result in complex scalars, which also leads to the third property, that if I take the inner product between psi and phi, what is the difference between the inner product between phi and psi? The moment I interchange their places, what I am essentially doing is I am simply taking the complex conjugate of that particular scalar product. So that means this is equal to this if I take the complex conjugate of this particular quantity. This is known as conjugate symmetry. And if I take an inner product of a quantum state with itself, in that kind of a situation, unless the state itself is a null vector, I will always end up getting an inner product that is greater than equal to 0, which also gives us a technique of measuring what is the length of that particular quantum state. Now, this length is kind of similar to the length of vectors that we have studied earlier, but vectors are something that we can visualize. Quantum states, however, it's more of an abstract mathematical concept, which is essentially equal to the inner product of a state with itself square root. All right, so these are some of the properties that the inner product in the context of quantum mechanics must maintain. Now, what is the physical significance of this kind of an inner product? That is what I want to explore in this particular video. So let me rub this space and write here. You remember I mentioned in the context of 3D vectors that if two vectors are perpendicular, their dot product is equal to 0. And if the dot product of two vectors is exactly equal to 1, it usually means that they are the same vectors with length equal to 1. So in that context, we have the concept of orthogonality and normalization for our abstract mathematical kets or quantum states. So for example, if I take the inner product between two states psi and phi, and if that inner product is equal to 1, it usually means that we are dealing with the same states. These are same states. So psi and phi are similar states, or measuring one would completely lead to the other. In that sense, if I take the inner product of a state with itself, and if that is equal to 1, it simply means that the state is normalized. Its length is exactly equal to 1. All right, so that's what happens when inner product is equal to 1. But what if the inner product of a state psi and phi is equal to 0? It means that these are completely dissimilar states. It means that if I measure psi it would automatically mean that I would not get phi. And if I measure phi, it would automatically mean that I would not get psi. So think of this as an example of tossing a coin. So we are all familiar with tossing a coin, right? If I toss a coin and I get heads, it simply means that I did not get tails. And if I get tails, it simply means that I did not get heads. So getting heads and getting tails are mutually exclusive. Both cannot happen at the same time. If one happens, the other did not. And if the other happens, the one did not. This is what it means when we take the inner product to be equal to 0. So in this context, the inner product of heads and tails is absolutely equal to 0. Alright, that is what it means when the inner product is equal to 0. We can take a similar example, for example, with respect to a quantum mechanical phenomena like electron spin. So whenever we measure the electron spin of a quantum mechanical system, if the electron spin comes out to be up, that means the electron has some sort of an angular momentum that has a very specific direction in the upward direction. It means that the electron spin is not down, right? But if the electron has a down spin, it means that it is not up spin, of course, in the Z representation, which by the theory here is represented by this specific calculation. If the inner product of an up spin and a down spin is taken as pure states, the inner product comes out to be 0, which means that if I measure the electron to have up spin, it definitely does not have down spin and vice versa. So this means that the inner product gives us some idea about measurements, right? So if I measure something and I discover that the state is in psi, it automatically means that the system is not in the state phi. That is what it means when the inner product is equal to 0. So these are kind of mutually exclusive states, or we can also say that the states are independent of one another. And this brings me to the most important part of the video, which is that the inner product has something to do with the measurement outcome of a quantum mechanical system. You see, if I have some kind of a physical system which exists in a given quantum state, and by now you must be familiar with the fact that a system before measurement can exist in a linear superposition of a large number of states or pure states. So let's suppose that I look at a system before measurement and the system exists in a state psi. But now if I make a measurement, I will not discover the system to exist in all the states all the time. I will discover it to make a choice. It's like the double slit interference experiment. You see, the electron before you make a measurement goes through both the slits, but the moment you actually look at the electron chooses which slit that it wants to go through. So if I make a measurement, it seems that the quantum state collapses onto one of the basis states or eigenstates or pure states, and the probability that I will get that particular basis state is given by the inner product of this manner, square of that. So this is the probability associated with that, where psi is more like a general mix superimposed state, where phi is more like a pure eigen state. So if a system exists in a state psi, theoretically speaking, at the moment of measurement, the system collapses onto a very specific basis state or an eigen state, and what the inner product mod square tells us is the probability associated with that sort of a collapse. So it tells us about probability. So it plays a very important role in the formulation of the quantum mechanical theory. The overlap between these two states tells us that if a system exists in a theoretical state before measurement, what is the likelihood that after measurement, the system will exist in one of the pure states. Now, to understand this, because this is a very crucial, important part of the quantum mechanical calculation, to understand this, I am going to give you a couple of examples. I will give you 3 distinct numerical examples, and if you understand these numerical examples, this whole thing is going to make perfect sense. So let us perform these quick numerical examples to understand this idea of an inner product in a better fashion. See, my objective in including a couple of problems is so that we can better understand what I mean by how the inner product plays a significant role in measurement outcomes in quantum mechanics. For this, I have the first problem. So this question says, let's suppose this is problem number 1. A potential well is prepared with the following quantum state. Psi x is equal to root over 2 upon 3 phi 1x plus root over 1 upon 3 phi 2x. What is the probability that if we make a measurement on the system will be in the ground state? Now, most of you must be familiar with the idea of potential wells, right? Infinite potential wells, finite potential wells. Now, there is a very unique case of a potential well that is prepared in some manner which has only 2 states. So the first state is phi 1, the second state is phi 2. For the sake of our calculation, let's assume that this is the original state of the system, that these are the 2 states and they both correspond to 2 distinct energy levels, right? Now, you know that in quantum mechanics, whenever we have some kind of a system, the system is capable of existing in a linear superposition of all the possibilities. So therefore, this is the quantum state, which is essentially a superposition of these basis states or eigenstates. According to the question, it is root 2 upon 3 phi 1x plus 1 upon root 3 phi 2x. Now, even though in quantum mechanical theory, a system can exist in all kinds of possible scenarios, the moment we make an observation, we find that the system is in any one of these levels, which means that if I actually make a measurement on the system, I will find that the particle in this system is either in energy level 1 or in energy level 2. The particle itself won't exist in both the energy levels at the same time upon measurement. So this is the uniqueness of quantum mechanics, that the theory allows a superposition of the states, but the moment we make a measurement, we call this the Copenhagen interpretation, that the system collapses onto one of the possible states. So the question is, what is the probability that if we make a measurement, the system will be in the ground state? So that is basically given by the inner product. So if we have a general state, let's suppose psi, and because the result is going to be a real number, it doesn't really matter if I put in the left hand side or the right hand side. This is the general state and this is the collapsed state phi 1. Then the probability that the system will collapse onto phi 1 is given by the inner product mod square. You see the role that inner product is playing here in this sort of a weird but a very relevant interpretation of how quantum mechanics affects measurements. So if I do this calculation, what do we get? Because we are dealing with mathematical functions, and I told you in wave mechanics, we have to take the inner product. So if I take the inner product, then I essentially end up getting phi 1x complex conjugate, and then within brackets I have root 2 upon 3 psi. I can write as phi 1x plus 1 upon root 3 phi 2x dx, of course between the widths of the well 0 to L. So if I simplify this, I will end up getting 2 upon root 2 upon 3. So of course there is a mod square here. Root 2 upon 3 integration of phi 1 star phi 1 dx and 1 upon root 3 integration of phi 1 star phi 2 dx. Now, because these are pure states, and in a quantum mechanical system, pure states are usually orthogonal. That means both of them are independent of one another. That means if I take an inner product of a pure state with respect to itself, I will get 1. And if I take the inner product of a pure state with a different pure state or an eigenstate, I will get 0. This simplifies our calculations to mod square, which comes out to be 2 upon 3. Therefore, this is equal to 66.67%. So if we prepare a quantum mechanical system in this manner, then the probability that if I make a measurement, the particle is going to be in the ground state is this much. That is the role that inner product plays in this particular problem. Now, these are the kinds of questions that are asked in various competitive examinations in India, whether it is Physics IIT JAM or CSIR NET or GATE Physics. And if you are one of those students who is preparing for these kinds of examinations, we have very dedicated batches, both live and recorded, at our platform elevateclasses.in. So if you are preparing for any of these examinations, you can check our website to find live as well as recorded courses for dedicated preparation towards various competitive examinations in India. Now, let's move ahead to the second problem, which is slightly different because it is in matrix representation. The second question says, an electron is in a spin state, chi is equal to, in column matrix, √3/2.5 in SZ representation. What is the probability of finding the Z component of the spin in negative Z direction? So the question basically gives us a state which is also prepared such that the electron spin is given by √3/2.5. This is in a similar fashion a mixed state because the electron in the SZ representation can exist either in the spin up or in the spin down direction, right? Those are the two basis states with respect to the Z axis. So if this is a mixed state, I can write down both these two states in this particular manner as a linear combination. So this can be written as √3/2, 1, 0 plus half 0, 1. Now, if you remember, I mentioned that 1, 0 and 0, 1 is usually used to represent spin up and spin down. So, therefore, this can be further simplified to be √3/2 spin up and half spin down. Now, the question says, what is the probability of finding the Z component of the spin in the negative Z direction? So basically, if I want to find the spin in the negative Z direction, I am interested in this eigenstate. So the probability is essentially equal to the spin down state, mixed state, inner product mod square. So I take the vector corresponding to spin down, which is 0, 1. I take the mixed state, which is given to us, that is √3/2.5 mod square. If I perform the calculations, it comes out to be half mod square, which comes out to be 1/4, which is nothing but 25%. That means in this kind of a system, if the system is prepared in this manner, the probability that if I make a measurement, the electron is going to have spin down is given by the inner product with spin down and the mixed state, that comes out to be 25%. So you see that whenever you have a quantum mechanical system, the moment you make a measurement, what is the probability or what is the likelihood that the system would collapse onto one specific state? That is given by the mod square of the inner product of the original state and the final collapse state. Now I want to do one more problem just to give you a further clarification on the matter. This kind of an inner product is also used for understanding time evolution of a state. So the next question says, a two-state quantum mechanical system has energy eigenvalues plus minus E corresponding to normalized eigenstates 1 and 2 kept respectively. At time t is equal to 0, the system is in a quantum state that is given in this manner. What is the probability that a system will be in the same state after time t equals h/6e? This is going to be a little bit of a lengthy problem. I'm not going to do all the mathematical calculations. I'm going to give you the results in just a moment. I'm just going to show you how it is formulated. So initially at time t is equal to 0, we have a quantum state which is given by psi is equal to 1 upon root 2, 1 ket, which seems like the ground state that corresponds to energy level minus E, and 1 upon root 2, 2 ket, which seems to be the first excited state that corresponds to energy level plus E. Now, if you want to study time evolution, all you have to do is you take the state. Here we are not performing a measurement. We are just looking at the time evolution. So at a different kind of a time period, after certain time has elapsed, what is going to be the state is simply given by, I just include the sort of a time function or the time component with respect to the state. So I have 1 upon root 2, 1 ket e to the power minus iota, and then you have minus e t upon h cross, and then I have 1 upon root 2, 2 ket e to the power minus iota e t upon h cross. This is the state after certain time interval has elapsed. The probability that I'm going to get this state after certain amount of time has elapsed, so originally this is at time t is equal to 0 and this is at some time interval t, is simply given by the inner product psi 0 psi t inner product mod square. The calculation is a little bit lengthy, so I'm going to include the mathematical steps here on the screen. So if you're interested, you can cross-check the mathematical steps with your calculations. The idea remains the same, that if a state is evolving from one given state to another state, what is the probability of that evolution is also given by the inner product of the initial and the final state. Now, before I wrap up this video, I want to make one final point about this inner product. You see, here we were talking about measurement outcomes. Now, of course, every time I make a measurement, it is not necessary that the system would collapse onto the same state. There is a probability associated with it. Therefore, what we are interested in quantum mechanics is what is called averages or expectation values, where also the inner product plays a very important role. For example, if I have any kind of a system where I want to measure the energy of that system, what I do is I take the Hamiltonian operator. I'm going to explain operator in detail in the next video, but operator is essentially a mathematical operator that acts on the ket, or the quantum state, to reveal some eigenvalue associated with that state. So the Hamiltonian acts on, let's suppose, a particular state, then we essentially get the energy eigenvalue associated with that particular state. What if the Hamiltonian acts on a different eigenstate or a pure state? We end up getting a different energy eigenvalue. So that means within a physical system, all possible energy levels are nothing but the eigenvalues corresponding to this kind of a Hamiltonian or energy eigenvalue equation, right? So I might have a large number of such equations. Now, what if I am interested in finding out the average of the energy measurements for a general state? So if a general state is given by a state psi, which is, let's suppose, a linear combination of a lot of eigenstates or basis states given in this particular manner, a summation or linear sum or a superposition of the basis states, then essentially psi and the inner product with the Hamiltonian acting on psi basically gives us the average of the energy. Because if you perform this calculation, you can do it yourself, you will end up getting all of these energy eigenvalues in this manner, C1 mod square E1. Okay, so C1 is the coefficient with respect to phi 1, and the energy eigenvalue of phi 1 is E1. And then you have C2 mod square phi 2. So C2 is the coefficient associated with phi 2, and E2 is, E2 here is the energy eigenvalue of phi 2, on and on. This is nothing but the average of energy. You see, quantum mechanics is not really capable of giving us an exact prediction of how a system is going to evolve, but it can give us a probabilistic outcome. It can give us an idea about the average of the measurements on a quantum mechanical system. So if I have a quantum mechanical system where I'm measuring the energy, every singular measurement performed on separate but similar systems might give us different results, but the average can be calculated by this kind of an inner product where we sandwich the operator, the Hamiltonian, with respect to the given case. So as you can see here, the concept of the inner product plays a very vital role in the architecture of this mathematical theory of quantum mechanics. And if you want to spend time performing various calculations in quantum mechanics, you need to have some idea of the concept of inner product, where to apply it, what it means. And I hope this video has given you some idea as to what is the role of the inner product in the measurement outcomes of quantum mechanics, or in the context of quantum mechanics. So that is all for today. I am Divya Jyotidas. This is For the Love of Physics. Thank you so much. Take care. Bye-bye.